Section 2 of Chapter 1 talks about three main topics: tangential quantities and centripetal acceleration and total acceleration. Let us have an object that rotates around itself, and I will be choosing two different points, point A and point B, on this rotating object. I will rotate it by 90 degrees, so point A will come here and point B will come here. I already know that every point on a rotating rigid object have the same angular quantities, same delta, theta, omega, and alpha. So the radius for A is smaller than the radius of B. If I pay attention, I can see that point A travels through a smaller arc length. So delta S of A is smaller than delta S of B. Have they traveled at the same time? Yes. So how is that possible? B has traveled a longer distance than A. They had the same time, if you remember. So delta S was distance traveled in a circular path, divided by time will be equal to speed. So I can say that the linear speed for A is less than the linear speed for B. So B is faster, that's why it travels more distance. And if I change the speed of A, speed of B will also change, but it will change with a greater rate. So if I divide it by time, I will get an acceleration. Acceleration of A will be smaller than acceleration of B. At this point, point B is trying to move upward. At this point, it's trying to move to the left. And you can check point A2. It is again up, it is less, again it is to the left. When we have a circle and a line meets this circle at a single point, this line is called as tangent. Since the linear quantities are tangent to the circular path, I will be calling it as tangential speed and tangential acceleration. I don't need this part, I will be deleting it. I will bring this one here, and I don't need this derivation anymore. So tangential speed is a linear quantity. Now the first equation that we had this year was delta theta is equal to delta S over R. So if I rearrange it, I will have delta S that is equal to delta theta multiplied by R. If I divide by delta time and divide by delta time, this will be equal to the tangential speed. This will be equal to angular speed multiplied by the radius. If Vt changes, omega also changes. So if I have a change in Vt, tangential speed, I will also have a change in angular speed. Multiply by R, divide both sides by delta time. Instead of this one, I will have acceleration, that's tangential. Instead of this one, I will have angular acceleration. So I can say that for a rotating object, every point will have different tangential quantities. Different delta S, different Vt, and different At. There's an important point here, which there's a question about it in Wazari and section review. If for a given point Vt increases, omega also increases. If Vt decreases, omega also decreases. So if the object speeds up, both of them will be positive. So positive, slow down, negative. So both are positive and negative together. And if there was a change in Vt, there's At. If there was a change in omega, there will be alpha. So whenever you have tangential acceleration, you always have angular acceleration. And if you don't have, if 8 is equal to 0, then alpha is also equal to 0. Remember that tangential acceleration is only and only about speeding up and slowing down. If you want to define tangential acceleration, you can define as the rate at which tangential speed change in the tangential direction. But if you remember, we said that velocity is composed of magnitude plus direction. Let's say that we have a car that moves in a circular path with a constant speed. So both omega and Vt are constant, so the magnitude is constant. If magnitude is constant, then tangential acceleration is equal to 0. Let's check direction. At this point, it moves to the left. At this point, it moves down. At this point, it moves to the right. At this point, it moves upward. So you can clearly say that any object that moves in a circular path will have a change in direction. If direction changes, velocity also changes. Whenever velocity changes, what do you have? You have acceleration. So now we have change in direction. So we have change in velocity. So we have acceleration. So this acceleration is because of change in direction of velocity. We'll call this as centripetal acceleration. And centripetal acceleration is only and only about change in direction. Acceleration is equal to change in velocity divided by delta time. We said that this is because of change in direction. So acceleration and delta v, they will have the same direction. So I will take vectors. It will be equal to v final minus v initial. I'm not talking about their magnitudes. I'm only talking about their directions. So I have only to take their directions. Now, let's say this is V initial and this is V final. This is V final and this is V initial. But do I need V initial itself? I don't need V initial. I need minus V initial. There's a vector rule which says that you can reverse a vector if you add a negative in front of it. And I can move a vector parallel to itself. So I can move this down. The direction of delta V will be from the tail of the first one to the head of the second one. So this is the direction of the resultant vector. When I put it on the circle, it is toward the center. So direction of delta V is toward the center. So centripetal acceleration will always also be toward the center. And we can find the magnitude of centripetal acceleration by v squared over r, or omega squared times r. Centripetal acceleration is a linear quantity because it is the change in the direction of the linear velocity. So the unit again is meter per second squared. What happens if I have a car that speeds up in a circular path? So I have a car that is speeding up in a circular path. So velocity is equal to magnitude plus direction. The magnitude is changing. It is a circular path. I have change in direction. And because of change in magnitude, I have tangential acceleration. Because of the change in direction, I have centripetal acceleration. So which one of these accelerations is the main acceleration? Both are the main acceleration. So what do we have to do? We have to find the total acceleration. Let's say that the object is rotating like that, and AT is always tangent, so this is AT. AC is always toward the center, this is AC. How can I add two vectors that are perpendicular to each other? By using Pythagorean theorem. So I will add them and I will get a total. And a total will be equal to square root of AT squared plus AC squared. Pythagorean theorem only helps us to find the magnitude of the resultant vector. How can we find the direction of the resultant vector? By using the tangent rule. So tan theta will be equal to opposite over adjacent. Why did I use this angle? Because the object is moving in this direction. So the angle must be between a total and the velocity, which is in the same direction as tangential acceleration. And tan theta will be equal to opposite is the one that is not attached. So AC is not attached, so it will be AC divided by adjacent, which is attached to theta, which is AT. If I rearrange it, theta is equal to tan inverse AC over AT. Now, this is called as non-uniform circular motion. So how can I have uniform circular motion? The example that we talked about a moment ago is actually uniform circular motion. When AT is equal to 0, it is called as uniform circular motion. This is uniform circular motion. In uniform circular motion, A total is equal to AC because AT is equal to 0. And you can say that since AC is perpendicular to VT, A total is equal to AC. So A total is actually perpendicular to tangential speed. So if a question tells you that an object moves in a circular path and the acceleration is perpendicular to its velocity, you have to know this acceleration is actually centripetal acceleration. It means Vt is constant, omega is constant. So it is in uniform circular motion.